prepare this notebook, I will just go through the notebook, and I also post the code to the link. So this is basically the a tutorial notebook we prepared to get to help the users get started. But we also have a detailed description of the how to run the package in terms of the command lines, how to install them, and a detailed example to use the supervised Jita clustering method. And the data is also prepared, and we have commands how to get the reproduce the results that we published with this package. But without further ado, I will just briefly talk about one possible way to use this package in a notebook. So the overall goal of this package is to facilitate the training of the graph neural network. The graph neural network is very flexible, so there are like many possible combinations or the way you can construct the graph neural network, but we just like try to connect the models that are proven or has been used in physics publications and in this repository, and also writing the code to monitor the matrix for classification and regression tasks. Later, we are going to add also that like a generative graph neural network based models in it. So the graph creation, there is basically two ways to do that. One is based on this NetworkX package. To do that, is just define the graph and add nodes, add edges. For example, I just add a node, 4 nodes, 0 to 3, and edges I just connected them in this way. You can make a plot like this and visualize it. This is called a directed graph. You see that the point node 2 is pointing to 3, 3 pointing to 0. This is directed, and you can do bidirectional so that the message they can pass through all the directions. The graph that normally we use is an attributed graph, meaning that the node has attributes. For example, node features. This node could be particle and has 4 vector, for example. And edges can also have their own attributes. For example, this can represent the distance between the 2 particles. Another attribute is the graph level attribute we call global attributes. That can be like event level information, could be part of conditions or number of particles in the event. To represent this, to present attributed directional graph, one can use this adjacency matrix to represent the edges, how the particles are connected, or a preferred way to construct the graph tuple is use a data dictionary. So the keyword we are using is following the GraphNets from the DeepMind package. Basically, we want to know how many nodes are there in this graph and how many edges, and the node attributes. So this will be with a dimension of number of nodes times node feature, number of node features, and similarly for edges. So this will be number of edges times edge features. Senders and receivers are basically to define each edge. So each edge, like which 2 node is belong to that edge. Global attributes is basically the global features of the graph. Once you have this data dictionary, you can just convert them to a graph. So in this tutorial, we take an example from a top tagger data set. You can download it from here, and I already downloaded it in local. I cannot run it in Biome because this more than 2 GB. But the data looks like this. Like each row is one event, and each particle has 4 vectors information. So this is the particle 0, this is particle 1, and so on and so forth. I can just loop over. I can just take like one event, one row, and try to make a graph. Because I know that there is how many features in the event, I can just quickly go over all these items, all these 4 pods to get to get the particle information and the particle for vectors. That's what will be my nodes, and my edges is just fully connected edges, bidirectional fully connected graph. In the end, my goal is to tell if this event is a QCD event or top quark event. So in my target graph, so this is my input graph that's basically have the particle information, but in my target graph, I tell this if this event is a 1 if it is the top tagger, 0 is if it is the QCD event. So I call this function to make a graphs, and I can visualize, check the dimensionality of the graph, and if it's set to XS. In the end, you just need 2 functions. One is called read, the other one is called meta graph to construct a data set. And this data set, once you define it, you can process the whole training set with to convert them to a native representation of the graph in TensorFlow. That can strongly facilitate the training speed. So I have done that, and once we have, and this like process will save all the TF records, that each record contains a certain number of events in each TF record in this folder. And then I just split them for 80% for training, 10% for validation, and 10% for testing. We have predefined models. I just go to the way that you would use them in here. So you can just take all the models, choose one of them, say global classifier, and define a loss, that global loss that you basically for classification, and define on optimizer. Once you have that, you can put them in all in a trainer. So the trainer we have many like default values one can just use as it is, but we also provide the handles to tune some hyperparameters once you find the results is not optimal. Once you construct the trainer, you can just start training and monitoring the status. So this is just one way to monitor. We also have the backend in TensorFlow. So in this output, there is also directory to monitor all the metrics that for the classification and regression. Yeah, that's the tutorial. Thank you.